Now, the Cauchy's convergence criteria. What is Cauchy's convergence criteria? Sequence of real numbers is converged. This is Cauchy's criteria. Cauchy criteria. Sequence of real numbers. Sequence of real numbers is convergent if and only if it is a Cauchy sequence. If and only if it is Cauchy. We already proved convergent sequence of real numbers is Cauchy. Convergent sequence of real numbers is Cauchy, and every Cauchy sequence is bounded. So we can say that the convergent sequence of real numbers is also bounded. Also we see that a bounded sequence need not be a Cauchy sequence. By using, that is proved by using an example. Minus 1 power n is a bounded sequence, but we know that that is not a Cauchy sequence. Now sequence of real, this is the Cauchy's criteria for convergence. Cauchy's convergence criteria. A sequence of real numbers is convergent, then surely it is Cauchy. A Cauchy sequence always convergent. Cauchy sequence of real numbers is always convergent, and convergent sequence of real numbers is always Cauchy. So this is the Cauchy's convergent criteria. How to prove this one? First part is already proven. Sequence of convergent sequence of real numbers is Cauchy. That is we already proved. Cauchy sequence of real numbers is convergent. We know that sequence xn is convergent sequence. That sequence xn is convergent. Then we know that, or we already proved that sequence xn is Cauchy. Okay. What about the reverse inclusion? This is a sequence of, suppose a real Cauchy sequence of real numbers, or sequence of real numbers, convergent sequence of real numbers. Convergent sequence, so convergence implies Cauchy. Convergence implies Cauchy. This is already proved. Suppose x equals xn is convergent, suppose it is convergent to x, then we already proved that it is nothing but a Cauchy. Okay. Now, that is already proved. What is the reverse inclusion? Cauchy sequence implies convergence. So let secant xn is Cauchy. Secant xn is Cauchy means secant xn is a Cauchy sequence. So that means for all epsilon is positive, there exists some k following en such that modulus of xn minus xn strictly less than some epsilon by 2 for all n comma m greater than or equals k. Okay. But we know that Cauchy sequence is always bounded. Cauchy implies bounded. This is already proved. Every Cauchy sequence of real numbers is bounded. Agreed? Okay. So clearly the sequence xn is a bounded sequence. Since why? Because it is a Cauchy sequence. This given secant xn is Cauchy, but we know that Cauchy sequence is bounded. Therefore secant xn of real numbers is a bounded sequence. Xn is bounded. But by Bolzano-Weierstrass theorem, what is Bolzano-Weierstrass theorem? Bolzano-Weierstrass theorem says that every bounded sequence of real numbers has a convergent subsequence. That is by Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem states that every bounded sequence of real numbers, every bounded sequence of real numbers has a convergent subsequence. Okay, convergent subsequence. Here we know that secant xn is a bounded sequence of real numbers. Why? Secant xn is Cauchy. Cauchy sequence is bounded. Therefore, secant xn is a bounded sequence of real numbers. But by Bolzano-Weierstrass theorem, every bounded sequence of real numbers is a convergent subsequence. Therefore, that means secant xn has a convergent subsequence. Has a convergent subsequence. So let x dash equals secant xn k be a convergent subsequence of x be a convergent subsequence of sequences. That means limit x and k or secant x and k. Secant x and k converges to some x star. Secant x and k converges to some x star means there exists some k1 for an n such that modulus of x and k minus x star strictly less than some epsilon by 2 for all n greater than for all n k greater than or equal some k1. Okay, that is why because of the definition of convergence. X and k converges to x star means for all epsilon is positive, there exists k1 for an n such that modulus of x and k minus x star less than epsilon by 2 for all n k greater than or equals k1. Okay. But xn is Cauchy. Xn is Cauchy means for all epsilon is positive, there exists k1 for an n such that modulus of xn minus xm less than epsilon by 2 for all n comma m greater than or equals k1. Agree. Put a k equals maximum of this k1 and k2. So these two results, these two conditions are held for n and m and nk. These two results. It is true for all n and m greater than or equals k, and this is true for all n greater than and k greater than or equals k. Okay, why? Because k is chosen in such a way that k is maximum of this k1 and k2. Since these two are held for this k1 and k2, and k is chosen for maximum of this k1 and k2, so these two arguments are held for this this natural number k, where k is maximum of this k1 and k2. Okay, right. Now what's our aim? Our assumption is secant xn is Cauchy, and what's our aim? Our aim is to show that this xn is convergent. So for consider modulus of xn minus x star. Modulus of xn minus x star. What is x star? X star will be the limit point of the subsequence xn k of xn. X star is the limit point of the sequence xn k. What is actually? What is actually the sequence xnk? Sequence xnk be a subsequence of sequence xn, and the sequence xnk converges to where? X star. Agreed. That is why because of Walsh-Weierstrass theorem. So now consider mod xn minus x star. Mod xn minus x star can be rewritten as mod xn minus xnk plus xnk minus x star. You can introduce minus xnk and plus xnk simultaneously. So which is less than or equals mod xn minus mod xnk plus mod xnk minus x star. Okay, but mod xn minus xm less than epsilon by 2 for all n comma m greater than or equals k. So mod xn minus instead of m, it is true for every nk. Therefore, it is strictly less than mod epsilon by 2. Again, by using this argument, it is again less than epsilon by 2. That means mod xn minus x star strictly less than epsilon for all n greater than or equals k. That means secant xn converges to where? Secant xn converges to x. This implies xn converges to x star. That means Cauchy sequence is convergent. So this is the Cauchy criteria. Every convergent sequence of real numbers is Cauchy, and every Cauchy sequence of real numbers is convergent. No doubt. Every Cauchy sequence of real numbers is convergent. Why? Because of this one. Every convergent sequence of real numbers is Cauchy. So combines these two results are known as the combining of these two results, which is known as the Cauchy's convergent criteria. Sequence of real numbers is convergent if and only if it is Cauchy. So these are the properties of a Cauchy sequence. That means every convergent sequence of real numbers is Cauchy, and every Cauchy sequence of real numbers is convergent. Every Cauchy sequence of real numbers is bounded, but a bounded sequence of real numbers need not be Cauchy. Now consider another important lemma, that is a bounded monotone increasing sequence is Cauchy sequence. Bounded monotone increasing sequence is Cauchy. Bounded monotone increasing sequence is a Cauchy sequence. Bounded monotone increasing sequence is a Cauchy sequence. How to prove this one? So for let x equals secant xn. X equals xn is bounded and a monotonically increasing sequence. Secant xn is bounded means by the completeness property it has a supremum. Okay, so let x equals the supremum of xn exists. So x equals supremum of secant xn where n fallen n. Now choose epsilon. Epsilon is positive. Then clearly x minus epsilon or x minus epsilon by 2 strictly less than x. X minus epsilon by 2 strictly less than x. Since x is the supremum of xn, clearly x minus any number less than x is not an upper bound. So by the definition of upper bound, we know that x minus epsilon by 2 is not an upper bound. Not an upper bound of the sequence xn where n fallen n. Okay, that means so there exists some x m naught. There exists some x m naught fallen set of all xn for all n fallen n such that yes, this x minus epsilon by 2 less than this x m naught less than this x means secant xn or less than this x plus epsilon by 2. Okay, so x minus epsilon by 2 less than xm naught or xm naught less than or equals x strictly less than x plus epsilon by 2. That is why because of the choice of this x. What is x? X is the supremum of xn. Why this supremum of xn exists? Because secant xn is bounded. Okay, secant xn is bounded. Supremum exists. Why? Because it has an bounded means it has by the completeness property it has a supremum. Let it be x. Since x is a supremum, no number less than x is an upper bound. Here epsilon is positive, so epsilon by 2 is a positive. So x minus epsilon by 2 is strictly less than x. Clearly x minus epsilon by 2 is not an upper bound of this set. Okay. Hence there exists some xm naught fall in this set such that x minus epsilon by 2 which is not an upper bound. So x minus epsilon by 2 is less than xm naught less than or equals x, that is strictly less than some x plus epsilon by 2. But what is xn? Again it is known that it is given that xn is strictly increasing. It is monotonically increasing. Xn is increasing means for all n greater than or equals some m naught. What is secant xn? Secant xn greater than or equals or secant xm naught less than or equals secant xn. Xm naught less than or equals, not secants. For all n greater than or equals m naught, we have x m naught less than or equals x. Why? Because secant xn is a monotonically increasing sequence. Agree? Since secant xn is monotonically increasing, it is xm naught less than or equals x. Clear? Therefore, we have x minus epsilon by 2 less than xm naught less than or equals xn less than xm. It is or less than or equals x means x plus epsilon by 2. Okay, that means x minus epsilon by 2 less than xn less than x plus epsilon by 2 from here. That means modulus of xn minus x strictly less than epsilon by 2. That means secant xn converges to x. Okay, secant xn converges to x. We know that every convergent sequence of real numbers is Cauchy. Therefore, the secant xn is Cauchy. Why? Because secant xn converges. We know that convergent sequence of real numbers is Cauchy, hence secant xn is Cauchy. Therefore, every monotonically increasing bounded sequence of real numbers is Cauchy sequence. That is heavily depends upon the definition of the supreme or the property of supreme. If x equals supreme of xn, x minus epsilon by 2 is not an upper bound. Therefore, there exists some xn not fall in this set which satisfies this condition. X minus epsilon by 2 less than xm naught less than or equals x plus epsilon by 2. But xn is a monotonically increasing sequence, means for all n greater than or equals m naught, xm naught less than or equals xn. So clearly x minus epsilon by 2 less than xm naught, but this xm naught less than or equals xn, but that is less than x plus epsilon by 2. So from here clearly secant xn minus mod xn minus x less than epsilon by 2. That means secant xn is converges to x. Secant xn is the convergent sequence of real numbers, but we already proved that every convergent sequence of real numbers is Cauchy, hence secant xn is Cauchy. That means bounded monotone increasing sequence of Cauchy sequence, bounded monotone increasing sequence of real numbers is a Cauchy sequence. Agreed? Thank you.